Download this code from codegive.com, link in the description below. OK, let's dive deep into the consistency of empirical risk minimization, ERM, which is a fundamental concept in statistical learning theory. This tutorial will explain the concept, its importance, the conditions for ERM consistency, and provide a code example to illustrate its practical implications. Lecture 21, Consistency of Empirical Risk Minimization, ERM. 1. Introduction, the goal of machine learning and ERM. At its core, machine learning aims to build models that generalize well from a finite training dataset to unseen data. We want our models to accurately predict or classify new examples that were not part of the training set. Empirical risk minimization, ERM. A common approach to achieve this goal is ERM. ERM works by selecting a hypothesis, a function, from a predefined hypothesis class H that minimizes the empirical risk. Empirical risk the average loss that the hypothesis makes on the training data. It estimates the expected loss based on the observed sample. Hypothesis class H, a collection of functions or models that the learning algorithm considers as potential solutions. Examples include linear models, decision trees, neural networks of a certain architecture, etc. 2. Formal definition of ERM. Let's formalize the concept. Training data D equals x_1, y_1, x_2, y_2, x_n, y_n, where x_i are the input features and y_i are the corresponding labels. We assume these are drawn IID from an unknown probability distribution P, x, y. Loss function L, h, x, y, which measures the cost of predicting h, x, when the true label is y. Common examples are squared error, for regression, and 0 to 1 loss, for classification. Empirical risk true risk, or expected risk. The true risk represents the expected loss of the hypothesis H over the entire distribution P, x, y. We can't compute it directly because we don't know P, x, y. ERM hypothesis the hypothesis H_n that minimizes the empirical risk. 3. The question, does ERM work? The concept of consistency. The crucial question is, if we minimize the empirical risk, does that guarantee that we are also minimizing the true risk? In other words, will the ERM hypothesis H_n generalize well to unseen data? This leads us to the concept of consistency. Consistency an ERM learning algorithm is said to be consistent if, as the amount of training data n approaches infinity, the risk of the ERM hypothesis converges to the best possible risk within the hypothesis class H. Formally, this means that with enough data, the performance of the ERM hypothesis will approach the best achievable performance given the choice of hypothesis class. 4. Why consistency matters. Guarantees generalization. Consistency provides a theoretical guarantee that, with enough data, the learning algorithm will produce a model that generalizes well. Justification for ERM. It justifies the ERM principle. If ERM is consistent, then minimizing the empirical risk is a reasonable strategy for finding a good model. Understanding limits. It highlights the limitations of a specific hypothesis class. If the hypothesis class is too restrictive, example only considering linear models when the true relationship is highly nonlinear, even a consistent ERM algorithm won't be able to achieve perfect accuracy. 5. Conditions for ERM consistency. Achieving consistency is not automatic. Certain conditions must be satisfied. The two most important conditions are uniform convergence the empirical risk should converge uniformly to the true risk for all hypotheses in the hypothesis class H. Formally, this means that the largest difference between the empirical and true risk across all hypotheses in H must shrink to zero as the sample size increases. Uniform convergence implies that the empirical risk is a reliable estimate of the true risk for all candidate models. Glavenko-Cantelli class a hypothesis class H that satisfies uniform convergence is called a Glavenko-Cantelli (GC) class. The GC theorem essentially states that uniform convergence is equivalent to the hypothesis class being a Glavenko-Cantelli class. 6. Factors affecting uniform convergence and consistency. Several factors affect whether a hypothesis class will satisfy uniform convergence and lead to consistency. Complexity of the hypothesis class more complex hypothesis classes are more likely to overfit the training data. Overfitting means that the empirical risk might be low, but the true risk is high because the model has learned the noise in the training data. A key measure of complexity is VC dimension, Vapnik-Chervonenkis dimension. Hypothesis classes with finite VC dimension are often GC classes. Sample size, n as mentioned earlier, a larger sample size generally improves the chances of uniform convergence and consistency. Bounded loss function if the loss function is bounded, example the 0 to 1 loss is always between 0 and 1, it helps to control the fluctuations between the empirical and true risk. 7. The role of VC dimension. The VC dimension is a measure of the capacity or complexity of a hypothesis class. Intuitively, it represents the maximum number of points that a hypothesis class can shatter. Shattering a set of points is said to be shattered by a hypothesis class if, for every possible labeling of those points, there exists a hypothesis in the class that correctly classifies all of them. VC dimension, D. The VC dimension of a hypothesis class H is the largest number D of points that can be shattered by H. If the class can shatter arbitrarily large sets, then its VC dimension is infinite. A fundamental result in statistical learning theory is the VC bound, which provides an upper bound on the generalization error, the difference between the true risk and the empirical risk, in terms of the VC dimension, the sample size, and the desired confidence level. 8. Code example, illustrating ERM and the impact of hypothesis class complexity. Here's a Python code example using scikit-learn to demonstrate ERM and the effect of hypothesis class complexity on generalization. We'll use a synthetic dataset and compare linear regression with a polynomial regression model. Explanation of the code *. 1. Data generation *. We create a synthetic dataset consisting of points sampled from a sine wave with added noise. This allows us to visualize the true underlying relationship and how well the models learn it. 2. Data splitting *. The dataset is split into training and testing sets. The training set is used to train the models, and the testing set is used to evaluate their performance on unseen data. 3. Hypothesis classes *. Linear regression *. A simple linear model with a low VC dimension. Polynomial regression *. A more complex model that can fit nonlinear relationships. The degree of the polynomial controls its complexity. Higher degree polynomials have higher VC dimension. For training, ERM the models are trained by minimizing the empirical risk, MSE, on the training data. The fit method of the scikit-learn models performs this optimization. 5. Evaluation *. The performance of the models is evaluated using the mean squared error, MSE, on both the training and testing sets. We compare the training MSE and the testing MSE to assess generalization. 6. Visualization *. The results are plotted to visually compare the performance of the two models. Expected observations *. Training MSE *. The polynomial model, with a higher degree, will likely have a lower training MSE than the linear model. This is because it can fit the training data more closely. Testing MSE *. The testing MSE may be higher for the polynomial model than the linear model, especially if the degree of the polynomial is too high. This indicates overfitting. The linear model, being simpler, might generalize better to unseen data. Overfitting If you increase the polynomial degree significantly, example to 10 or higher, you'll likely observe a large gap between the training and testing MSE for the polynomial model, illustrating clear overfitting. 9. Key takeaways from the code example. Bias variance trade-off This code illustrates the bias variance trade-off. The linear model has high bias, it can't fit the nonlinear relationship well, but low variance, it's not very sensitive to the specific training data. The high-degree polynomial model has low bias, it can fit the training data very well, but high variance, it's very sensitive to the training data and may overfit. Importance of regularization In practice, techniques like regularization, example L1 or L2 regularization, are used to control the complexity of models and prevent overfitting. Regularization adds a penalty term to the loss function that discourages complex models. Model selection Proper model selection techniques, such as cross-validation, are essential for choosing the right hypothesis class and hyperparameters to minimize the generalization error. 10. General strategies for achieving consistency in practice. Choose a suitable hypothesis class. Select a hypothesis class that is expressive enough to capture the underlying patterns in the data but not so complex that it overfits. This often involves balancing bias and variance. Use regularization. Apply regularization techniques to prevent overfitting, especially when using complex models. Collect enough data. Ensure that you have a sufficient amount of training data to reliably estimate the true risk and avoid overfitting. Cross-validation. Employ cross-validation to estimate the generalization error and tune hyperparameters. Feature engineering. Carefully design features that are relevant to the problem and can help the model learn more effectively. 11. Beyond VC dimension, other measures of complexity. While VC dimension is a powerful concept, other measures of complexity are also important in statistical learning theory, especially for models with infinite VC dimension, example neural networks. Rademacher complexity measures the ability of a hypothesis class to fit random noise. Lower Rademacher complexity indicates better generalization. Covering numbers measure the size of the smallest set of hypotheses needed to cover the hypothesis class. Smaller covering numbers imply better generalization. Information complexity related to the number of bits needed to describe the hypothesis class. 12. Limitations of consistency results. Asymptotic results. Consistency results are asymptotic, meaning they hold as the sample size approaches infinity. In practice, we always have a finite amount of data. Computational considerations. ERM might be computationally intractable for some hypothesis classes. Finding the exact minimizer of the empirical risk might be difficult or impossible. Practical algorithms often find approximate solutions. Model misspecification. Consistency results assume that the true underlying function is within the hypothesis class. If the true function is not in the hypothesis class, Model misspecification. Even a consistent ERM algorithm won't be able to achieve perfect accuracy. 13. Conclusion. Consistency of ERM is a cornerstone of statistical learning theory. It provides a theoretical foundation for the idea that minimizing the empirical risk can lead to good generalization. Understanding the conditions for consistency, such as uniform convergence, and factors that affect it, such as hypothesis class complexity, is crucial for designing effective machine learning algorithms. The code example illustrates the practical implications of these concepts and the importance of the bias-variance trade-off. By carefully considering these factors, we can build models that generalize well and perform reliably on unseen data. Remember that, while consistency provides valuable theoretical guarantees, it's important to be aware of its limitations and to use practical techniques like regularization and cross-validation to improve generalization performance in real-world applications.